Here we have function fx, which is x squared plus 4x plus 5. And when x is negative 1, fx becomes minimal. The minimal value is 1. This uppercase n is total number of iterations. Iteration is a vector that goes from 0 up to n minus 1. And xopt is optimal x candidate, and it is a vector with n components. And our first candidate value is 0, and dx is a delta x, which is 0.01, and c is a constant value that becomes a part of our step size, and this c is 0.1. Now we have a for loop. Lowercase n is iteration index. And here we have slope. This slope is same as the slope we saw in the gradient descent method. This term Hess comes from what's called a Hessian matrix. In our example, we are dealing with x and fx, but in some cases, we may deal with function with multiple variables, and we need to do some multi-dimensional computation, and our second derivative in that case may become a matrix. But in this case, we are not dealing with multidimensional computation, so no matrix is used. But still, I want to call this Hess. Again, this is a second derivative at xopt of n. Now here we have an equation very similar to gradient descent. In gradient descent equation, we had mu here, which is step size. But now the step size is c over Hess. So this c is a constant here, which is 0.1. The step size is inversely proportional to this second derivative. And let's run the code and see what we get. Okay, so we start from 0, and after like 60 iterations, we reach this optimal value for x, which is negative 2. Now, what if we increase this c value from 0.1 to 0.5, which means we are basically increasing the step size, so we may reach our target faster. Let's run the code. And now you see that we reach negative 2 around like 10, so which is good. Change this c value to 1. So we are increasing our step size, and let's run the code. Okay, maybe we want to decrease number of iterations. Let's make it say 5, right again. And interestingly, we reach negative 2 in the first iteration. So here it is 1.0. We have 0.5 here and 1.0 here. Extremely fast. But there's a cost because we need to compute this second derivative. This is Newton's method.